So, is everything okay?
Yeah, very good.
Okay, thank you, Professor Reddy, for the very nice introduction. Also, I would like to thank Professor Reddy for inviting me and having me again as a speaker at the Geoenvironmental Engineering Research Webinar Series. Dear guests, dear colleagues, my today's presentation is going to be about climate resilient infrastructure in water sector. And the presentation is generally consisted of two parts. The first part is about some background about climate resilient infrastructure. And the second part, during the second part, I'm going to present a case study about climate change adaptation for an irrigation system that's located in Skopje Valley, and also a case study about climate change adaptation for the water supply system for the city of Skopje. Over the last decade, and especially during last several years, climate resilience of the infrastructure is becoming one of the major considerations and areas of combating against climate change impacts. Climate change impacts on the infrastructure may be a result of the chronic stresses of the climate and also as a result of the acute shocks. Chronic stresses are mainly the hazards that happen as a result of long-term changes in average climatic conditions, like long-term changes of average temperature, sea level rise, or continuous erosion of the coast. While acute shocks, they happen as a result of the hazards that are happening as a result of the increased intensity or the recurrence of extreme weather events, like we have the floods, flash floods, droughts, hurricanes, and other severe extreme storms. This climate change changes have impact on the infrastructure in terms of damaging the physical infrastructure or also disrupting the operation and services provided by this infrastructure. But when we come to the climate change impact to the infrastructure of the water sector, the main factors that are contributing to this climate change impacts are the temperature changes and also the changing pattern of the precipitation. The temperature changes, they lead to the increased need for water treatment due to the water quality deterioration. This increased need for water treatment is a result either by the drought condition or the flood impacts. The drought conditions mainly lead to water scarcity and to reduced supply. Also, they lead to reduced water levels and also reduced minimal capacity of the groundwaters. That's how they increase the concentration. That's how the concentration of pollutants becomes increased in the water bodies. Also, the higher temperatures, they lead to some conditions for increased waterborne pathogens in the water supply systems. On the contrary of the drought condition, also floods cause damages to the infrastructure, physical infrastructure of the facilities, and subsequent health, environmental, and economic impacts. Also, heavy rainfalls, high-intensity rainfalls are associated with high-intensity surface runoff. They increase the loading of sediments and contaminants into the surface water. Surface water is infiltrating into the groundwater, and that's how the propagation of contaminants is transported through the groundwaters. Also, the deterioration of the quality by the floods is caused by overflow and contamination from the sewage systems. Temperature changes also lead to the increased evaporation from reservoirs. In climate change conditions, according to the climate scenarios predictions, we expect higher temperatures, higher solar radiation. These parameters, higher values of solar radiation and evaporation, and also higher wind speeds, they increase the reference evapotranspiration that indirectly has an impact on the crop water requirements. Higher values in climate change conditions for crop water requirements and lower values of the available resources in terms of rainfall, precipitation, and groundwaters lead to increased water demands, particularly for the irrigation water requirements. The other major factor for the causing climate serious impacts on the infrastructure in the water sector is the changing pattern of precipitation. The changing pattern of precipitation mainly causes more risk for overflooding or overtopping of the river training facilities of the river embankments. Also, due to this changing pattern of precipitation, the standard of the protection offered by flood protection or by river training facilities is being decreased, because when we planned, designed, and constructed the river training facilities for flood protection, they were designed to other standards according to the data that were, let's say, with much lower values than the ones that we're experiencing nowadays, and especially in climate change conditions in the forthcoming period. Also, the changing pattern of precipitation causes disruptions of the supply system in cases of water scarcity, and some also physical damages to facilities like water intake structures that are located on the rivers. Also, they also cause physical damages of the water wastewater treatment plants. Changing pattern of precipitation also causes overflow of from the stormwater infrastructure in urban areas, when the stormwater infrastructure, when we have separate sewage systems. Also, this may be a case when we have mixed sewage system, when we to have a overflow from the sewage system. This overflow causes flooding of the urban areas and also contamination of surface, also in groundwaters. So it's very important to analyze why this overflow happens. The maximal surface runoff or the discharge that happens as a result of a higher intensity rainfall is dependent on the runoff coefficient and rainfall intensity for a, let's say, constant drainage area. If we keep the drainage area constant, then this discharge is a function only on the runoff coefficient and the rainfall intensity. Taking into consideration the runoff coefficient that represents the fraction of the rainfall that is converted into the runoff, it can be noticed that this runoff coefficients having very low values in cases of urban areas when we have vegetation. But in cities, in urban areas where the surface of the ground is nearly impassable, the values of this runoff coefficient are very high. That's why in rural areas, nearly the largest portion of the rainfall infiltrates into the soil, and there is only a small portion that is transformed into surface runoff. And that's why the discharges are low. On the opposite side, in urban areas, the largest portion of the rainfall is transformed into the surface runoff, causing higher discharges. And it's very also important to know that these large discharges in urban areas happen in quite shorter period from the start of the rainfall compared to the period of occurrence of maximal discharge for the rural areas. The other parameter that's, let's say, major, the parameter that the flood or the discharge is dependent on is the intensity of the rainfall. For the intensity of the rainfall, we usually develop this curve, intensity, duration, probability, and these are very important curves for planning, designing of all this infrastructure in the water sector. That's why it's very important in changing climate to keep these curves updated. So we have here on the picture on the left that these curves constructed for the city of Skopje, but they are constructed there for the period in 1990s. Well, this period does not consist data about climate change in their records, because as we can see on the picture on the right side, it is a time series of the maximal annual precipitation for the period till 2020 till nowadays, and we can see that the maximal events, the events with maximal annual precipitation per day are happening during the last decade. That's why we have to keep these curves updated, so we can also incorporate climate changes of the main parameters like precipitation and probability of occurrence within this data that are very important for designing of climate resilient infrastructure. So what is climate resilient infrastructure? It is the infrastructure of facilities, assets that are planned, designed, built, and operated in a way that anticipate, prepare, and adapt for changing climate conditions. It's very important that this infrastructure responds and recovers rapidly from all these disruptions that are caused by climate change. It's very important to involve this adaptation and resilience of the infrastructure in all the phases of the project life, or of the project, or of the infrastructure life. That's why we have to analyze what is the life of a project and how are we going to integrate climate change adaptation into this project development cycle. Project development is presented on this picture as let's say a straight process. However, it happened in the practice that sometimes some phases of this project development cycle have to be repeated, or let's say some projects have to go through reiterations through some of these phases, and also is applied to the climate change adaptations and assessment and risk assessments that are going to be undertaken during this project development process. So starting from the earliest phases or pre-planning phases, when we have strategy building or spatial planning and urban planning, or development of pre-feasibility studies, like also a strategic environmental impact assessment. And at this level, only high-level vulnerability and risk assessment has been performed. It's performed in order to exclude all these high-risk projects. The next step of the project development is the first step of the project development, which is about feasibility analysis. This feasibility analysis step includes conceptual design of the projects, analysis of the alternatives, maybe site selections, or maybe some technology selections. And it's very important through this phase that the early phases of the screening and scoping of the environmental impact assessment are being addressed. The other phase of the design project is the design phase of the project, where the main design is being developed and associated with cost benefits analysis and the development of the full environmental impact assessment. When the design phases are finished, the construction of the project is started and finished. Also installation of the equipment, and all the project is gone through the supervision. Then the project phase, the project operation is the next phase, and the last phase of the life of the project is the commission. Where do we start with climate change adaptation? We already said that in the pre-project, we have high-level vulnerability and risk assessment of climate considerations. Well, starting with the feasibility analysis, where the foundation of the assessment already being set. And starting with the feasibility and the design process, then vulnerability is being assessed, and also risks for climate change impact is being assessed. Vulnerability assessment is a result mainly on the sensitivity of the project. How can we address, and what does sensitivity of the project means? The sensitivity of the project is dependent on the type of the project that is going to be constructed, and also about the local conditions, conditions at the location of the location of the project. And also vulnerability is dependent on the exposure. It's dependent on the time that the particular project is going to be exposed to the particular climate impact. That's how the vulnerability is being assessed. Risk is being assessed as a result of the probability of occurrence of the particular climate impact, and also the severity of this, or the magnitude of this climate impact. When we define the vulnerability assessment and the risk assessment, in case we have significant risks all these significant risks should be managed and reduced to some acceptable level. The aim is to increase the resilience of the project and to adapt the project to climate change. And in this phase, when the adaptation is being proposed and the type of adaptation, the adaptation measures are being proposed, and they are mainly consisted of two broad categories. They can be classified in two broad categories. The first category is the structural measures, which include flood defense, protection systems, construct some urban stormwater infrastructure, which is very important for some for urban areas. Also, in the group of structural measures, some measures that reduce the surface runoff are implemented, like using permeable paving surfaces that reduce runoff during high-intensity rainfall. Also, between this measure is to implement some green infrastructure to combat urban flooding, and also some nature-based solution in nowadays. These are some structural or measures that we construct to cope with these significant risks. Besides this structural, the other type of measures are the non-structural management, which include adapting water governance, adaptation of some operational practices, for example, of the capacity of artificial reservoirs to some flood or drought conditions. It means how we're going to operate with the water quantities that are in the reservoir in case we have floods or in cases when we have drought conditions. Also some early warning systems and also some monitoring of existing facilities or assets. These adaptation measures and all this risk assessment and also all the assessments are performed during the feasibility phases and also during the design project phase. When we are finished with adaptation measures. This process development and process of vulnerability assessment, risk assessment, and proposal of adaptation measures is going to be presented for a case study for climate change adaptations. For the first case study is about irrigation system that is located in Skopje Valley, and the second case study is about water supply system for the city of Skopje. They are both located in the Republic of North Macedonia. The aim of the research is to perform high-level vulnerability assessment of the climate change impact on irrigation water requirements and on drinking water supply. Also, the aim was to assess availability of the current water resources. Are there enough water resources to meet the increased demands for irrigation and increased demands for drinking water supply in the future period under climate change conditions, and in the end to propose some adaptation measures. Both case studies are located within the Skopje Valley, within the capital. Skopje is the capital Republic of North Macedonia, and the city of Skopje lies in the Skopje Valley that's located in the northern part of the country. Republic of North Macedonia is on the Balkan Peninsula within the Europe. And here on this picture, we see the topographical conditions of the area. From this picture, we can see that there is a lowland, there is a valley, lowland valley that's surrounded by high mountains. Through the valley, there is a river Varda, that flows through the valley. Taking into consideration the geographical location of the area and also the terrain, the climate is continental and Mediterranean, and the lower parts of the valley, they are experiencing very hot and dry summer periods. The average temperature is nearly 13 degrees Celsius. There are short heat waves. They last several days, and they are more frequent during last 10 years. What is really important that the precipitations, the annual sum of precipitation is very low. It's nearly 500 millimeters per year. we have really dry periods. They appear during the summer period, during the summer season from July to September, and sometimes they can last more than 60 days. But most of the precipitation happen during winter season and in autumn, while only a small portion of the precipitation is in spring, in March and May. The next pictures presenting the time scale, the time series of the precipitation. It's interesting. There are two pictures. The first one presenting the annual sum of precipitation for the period from 1961 to 2005, and we see that annual trend of precipitation is decreasing. But if we take into consideration most recent years, we see that the annual sum of precipitation is having an increasing trend. That is happening as a result that the decades during 70s, 80s, and 90s were decades that were characterized by drought conditions, while the last 2 decades there is a lot of precipitation. The average annual sum of temperature. The average annual temperature for the city is having an increasing trend for the whole period of the records. Well, the index of drought that has been calculated using the Martinez formula is estimating that the climate is dry and semi-arid climate. So what is the methodology? How was all this research performed? In general, I will present first the general methodology. To forecast the irrigation water requirements and also drinking water supply for the forthcoming period, the first step was to generate series of monthly and annual temperature data for the climate change scenarios in the future. Then the second step was to analyze the climate change impact on the irrigation water requirements, to use the data and predict the climate change impacts in climate change scenarios. Then the next step was to perform also the climate change impact on the drinking water demands in the future, also using the same climate data that are generated. And also the next step was to link the demands for the water with the available water resources for irrigation, and also to link the demands for water supply and to the available water resources for water supply. And in the end, to propose adaptation measures. The first step, the generating synthetic sequence of climate series, is based on the data for the climate, for the changing of the precipitation and temperatures as main climate data. And they are used from the climate change scenarios that were performed within the Third National Communication on Climate Change that was performed in 2014. Using this data, and this data for the period 2025-2100, this data were used to generate synthetic sequences of climate series. First, the data for 2025 and 2050 from this climate change scenario that were on the results from the climate change scenario. The data were presented as seasonal values, but we needed to expand this seasonal data into the monthly values. That's why we developed a 4-degree polynomial equations. And that's how we expanded the seasonal data into monthly data for year 2025 and 2050. After that, these monthly values for 2025 and 2050, we needed to interpolate this data within each year within the forecasted period. And when we got the data, these data were, the results were in degrees Celsius, and for the precipitation in change in percentage, like we see here the results. For example, we see the results for starting for 2015 till 2050 year, and for the increasing of maximal temperature, and we see that maximal increase of temperature happens during the warmest part of the year. In 2050, we are expecting 3 degrees Celsius increase of the temperature. And also for the precipitation, the maximal decrease happens during the warmest part of the year, and the maximal decrease is expecting to be minus 2.5% of the precipitation. As these data are only present the difference, these data are being added to the historical values of climate data to the precipitation and temperature, and how the data, forecasted data for precipitation and temperature for the forthcoming period are being already estimated. With these data are using to forecast the forthcoming irrigation water requirements and also drinking water requirements in climate change conditions. First, the climate change impact on irrigation water requirements has been researched using data for historical data for the meteorological station that's in the area, and also agricultural data from relevant sources. Using this data, the methodology for estimation of irrigation water requirements was applied. The first step includes a calculation of irrigation water requirements for the historical period of 45 years, namely from 1961 till 2005. And these values were calculated using CropWatts software, Food and Agriculture Organization software, that's CropWatt. And using this software, all these water requirements for the time series in the past were calculated. And after that, using the generated data of precipitation and temperature in climate change conditions, synthetic data series for irrigation water requirements are generated for 2016 till 2050. The results are presented for the historical period on this picture. And due to the large amount of the data, all the results were presented with 25, 50, and 75% of empirical probability. And also predicted irrigation water requirements are predicted for the same time period with the same probability. The data are presented with the same probability. The results are indicating that during that predicted crop water requirements in climate changing conditions are extremely high during summer season. And that predicted climate changes until 2050 may increase the irrigation water requirements for nearly 8%. So the next phase is to ask the question: if we have estimated that there will be 8% of increase of irrigation water requirements, how are these quantities going to be met? What are the available resources? Well, at the present moment, because all the irrigation area is very small, farmers are not using the total capacity of the agricultural land. And all the water needed for irrigation is being supplied by the surface waters and also using some ground waters. In the future, if there is a need to irrigate the whole planet agricultural land, there is an artificial reservoir upstream of the distributary to the river Vardar. And there is an artificial reservoir which is planned, designed, and constructed to have water quantities, reserved water quantities for irrigation of the lowland, of the agricultural land within the Skopje Valley. Then, using the second case study was to analyze what is the climate change impact on the drinking water supply. What data did we use to do this research? We used the same climate data for the historical period, data for the same main meteorological station in the city. And also we used water supply data, namely the data about delivered water quantities for drinking water supply of population. We used only the data that were available, used 300 data for the period 1990 till 2015. And also we use data about available water resources. What was the methodology that we used? First, we had to analyze what is the impact of the increasing temperature and decrease of the precipitation in climate change conditions on the water supply demands. That's why we had to link the water supply demands, or this data that we had for the drinking water supply, this historical data, to link them with the precipitation and temperatures with climate parameters. But we know that water supply data are dependent also on the number of population. That's why multi-regression model was defined with a set of independent variables. One variable was the number of population for the present time and 3 time sequences before, and also it was linked with precipitation and average air temperature for the same time sets. This multi-regression model then was normalized. Then these time series were normalized using regression model in the range between 0 and 1. Statistical tests were performed on the transform model. And how was the calibration validation of the model performed? It was the first part, we had 300 data from this period. They were divided into 2 parts, and the first part was used for testing for forming the model, for calibration of the model, while the second part of 150 data was used for testing and validation of the adaptability of the model. When the model has been tested and validated, then the forecast of future production of water was performed using this model, and also using the number of population variable, also the temperature, precipitation. These were the generated data, climate data for the forthcoming period 2025-2050. But to analyze the impact of the climate changes, namely changing of temperature and precipitation of this on the water supply, 2 scenarios were developed. First scenario assumed that the number of population until 2050 remains nearly the same, which means if we don't change the number of population, then the water demand is dependent only on the climate parameters like precipitation and temperatures. And the second scenario assumes increase of the number of population on average annual rate on increase of 0.58%. And all these scenarios use the already generated climate data. The results are presented here for the first scenario for the dependency on the water production on this time series until 2050. The first part, the left part of the picture, we have graphs presenting measured and modeled water quantities. And the second part, starting from 2016 to 2050, we have only the modeled water quantities. In case in case of the first scenario, when we have constant number of population, there is an increase of water demands of nearly 12%, and this increase is only is due to the climate change conditions. For the second scenario, when we have an increase of the number of population, the total increase of the water demands in the future is nearly 26%, and it's mainly due to the increase of the number of population. So what are the available resources for supplying this increased water demands for water supply of population in the future? The available resources is a spring that's having a large capacity. It's near the capital. And also some small quantities of water supply, especially during the summer period, are met by using groundwater resources. The results of these assessments are showing that for the first scenario, when we have climate change condition and no increase on number of population, which is not let's say, a real case scenario, the current paternal water supply of consumers can be met by the available resources, which is not the case for the second scenario, when the increase of number of population. Well, in that case, we need to use the maximal capacities of the spring and also of groundwaters to meet the maximal forecasted production. As a result of all these assessments, some adaptation measures are being proposed. First group of the adaptation measures, let's say indirect measures, that are mainly measures associated with the policy. And the first measure that has been proposed is to mainstream climate change aspects in spatial planning and urban planning documents. It's a very important question. And right now, the country is in the phase of implementing this adaptation measure, because a new spatial plan is under development, and it's, according to the methodology proposed, is going to involve climate change into the spatial planning. The second adaptation measure was to update the study of rainfall intensity duration frequency curves under the changing climate, and also this measure has been fulfilled. And the third measure is to raise awareness to increase the level of education of farmers for water-saving irrigation techniques. For example, instead of using surface irrigation methods, to use some water-saving techniques like drip or maybe some types of sprinkle irrigation. In the group of direct measures, the measures that were proposed is to implement measures to use alternative sources of water or groundwater for irrigation of green areas and washing streets and public areas within the city, not to put so much pressure on the main water sources for water supply, like the spring and like the spring. The other measure was to construct system for reuse of industrial water within major industrial capacities where applicable, which means that we don't, in case where this is applicable, we don't need to use anymore the water from the spring for industrial purposes. Also, to reduce the surface runoff, a measure was proposed to do some forestation of bare and unused land, so we can increase the infiltration into the soil, and also some measures about redesigning and reconstruction of the rural drainage systems. These are all these measures and all this part of my presentation that's connected with the title. Before I say I finish my presentation, I would like to mention a very important projects showing us some really important projects about climate that present a really climate resilient infrastructure. The first one project is the Tunnel and Reservoir Plan. It might be maybe the largest civil engineering project on Earth that's is being constructed to protect from flooding the area of Cook County, and also to preserve the quality of the rivers, of the water bodies within the county, and also to preserve the quality of the Michigan Lake as a very large and very significant water supply. So I would recommend all the participants of this webinar to maybe take a further information about this very important and very significant climate resilient project. And also, while I was preparing my presentation, I looked at the USC data and USC commitment to combat climate changes, and they have a commitment. They have a commitment that they will become neutral. They will become neutral till 2050, and that's why they have developed a climate action implementation plan. And this climate action implementation plan also involves some climate resilience, strategy. It's a very significant effort of the USA in combating against climate changes. For example, they have some green stormwater infrastructure implementation plan, and it's and they develop and they design and they go within this climate action implementation plan. And at the end, I would like to thank all of you for your attention, and if you have any other questions, and just to remind you that one of these largest civil engineering projects on work was organized a field visit to this Metropolitan Water Reclamation District of Greater Chicago during the 2019. It was the second conference of environmental geotechnology, recycled waste materials, and sustainable engineering conference. So thank you for your attentions. And if you have any questions, I'm willing to answer.
Thank you. Thank you.